Good morning, friends. In the previous videos, we discussed about designing an LRU cache, least recently used cache, which uses classic data structures. So we used a W linked list and a hash map, and it should also be thread safe. So we discussed all about how to insert a node with a key value pair, how to get the value, and how to find the least recently used and then further delete it, and all the operations in a map. Most recently, I have got a comment that this is not the get operation that we are using here, get value by key. This is not thread safe. So let's see about it. So the get operation is not a simple read operation. It's doing modifications in our DLL. And since we are only taking a read lock in the get operation, so multiple operations can actually, because we are not only just reading the data, we are trying to modify the underlying data structure. So this is why it should not be thread safe, because if we are trying to just use a read lock and using that read lock, we are also manipulating the data, then definitely there would be a race condition. So I think this comment is perfectly valid, because if we look at the read write lock interface, so it actually creates a pair of locks, one for read only operations, which we call as read lock, and one for writing. And the basic idea is that if there is no thread which is currently writing or manipulating the underlying critical section, whether it's a data structure or whatever block of code, if that critical section is being manipulated or written by a single thread which is writing, in that case, all the read locks has to be implemented. I mean, there should be no reader which can read the data at that time. Once the writer thread has written or manipulated the data, the critical section of our code, only then all the read after that only and when it's release that lock, that write lock, only then all the readers can read it. Which means that if there is no thread writing at the moment, there can be multiple threads which can read the data unless they are not manipulating it. Let's go back to our design again. I mean, we have already discussed in details about all the other operations, but let's focus on this get operation. So in this get value by key, right? So whenever we call this get method, so first of all, we look up that node in hash table and return the node value. So if I go through this simple design, so we are maintaining this two like linked list, and which is a W linked list, which means that each node has having a previous and next node. For example, C would be having a previous link of this node D, and the next link as B. And our most recently node would be always at the pointing to the head of the linked list, and the least recently would be at the tail. So whenever we want to like evict, use the eviction algorithm where we need to delete the least recent, we can only go to this linked list and just remove whatever is pointed by the tail, which is at the end. This is our least recently, and this is what needs to be removed. And our hash table, which is just maintaining the key and the node, because node is just treat node as a pair of key and value. So whenever you want to quickly look up in the O1 time, I mean in the constant time, we want to look up our node, we can just use this key and get it from the hash table. This is the purpose of hash table. And the least LRU algorithm has been implemented by this linked list. So if we look at this get operation, first of all, whenever we want to get a particular node value, we can simply call the get method from the hash table and return the node value. But here it is not just the read operation. We are actually updating our linked list. Update most recently used item by moving the node to front head of linked list. This is the manipulation operation, right? It means that it actually breaks our read write logic that we have written before. So now let's back to the code and see. So as mentioned that we are using this linked list node with this key value pair, having the next and the previous link, and just directly jump to the get method. So here I'm using this read write lock, right? So in the get method, we are just using this read lock at the beginning. We perform all the operation, and finally, in the finally block, we are releasing this lock. But as mentioned that this is the part where we are actually manipulating our database. We are writing or changing our database. Our data like folders. For example, we are updating our hash. I think we are not doing anything for the hash table, but we are definitely changing our linked list node, the linked list that we are creating, because we are removing from the node and then we are inserting at the front of the linked list. So in other ways, I mean, if we talk about this again, so what we are doing is that whenever we are doing a get operations, for example, we are using get for say C. So C is in the middle. So after this C has been returned, I mean, before that, after that, we have to update this linked list. We have to move C to the head, because the get operation, it will make this C node as the most recently node, and that's why it has to be moved to the head. So this is the manipulation, or this is the mutation that we are doing in our linked list, which is not thread safe because we are only using the read lock. Now, how to solve this problem? As we have identified that this is the critical section where we are manipulating our uh, list head node and the tail head link. These are the two objects which we are manipulating here, and that's why it cannot be thread safe by just using our read log. If you just go through the methods again, so here we can see that remove from linked list. For this is the step where we are trying to like remove say C element from the current position and then move it to the head. That is the second method. So here this is just removing it. And once we remove it, what we need to do is that if you're removing C, then the pointer D, the next pointer for D should be pointing to B. And similarly for the previous node pointer for B should be D. So these are the two things that we need to do. This is what we are taking care of. And our class members, list tail node and list head node. These are the two critical section part where we need to make it thread safe. So this is being eliminated, and similarly for say insert at front of linked list. So after we remove it, we need to insert that node to the front of the linked list. For that also, we are manipulating our list head node and list tail node. If I go through this, these are the two pointers, head node and tail node in our linked list. So as we know, this is the part. So I think the fix should be simple. I think the most naive way is to create an object log and guard this method. So this is what I'm going to do it here. So what I will do is that I will create a private final object, say object lock is equal to new object, because every Java Pojo object is has got a mutex lock inside it. So here, just guard this whole with this object lock and just mark it here. Okay. So by this, we are just synchronizing this part, that whenever we are trying to manipulate our list head node and list tail node objects, then we have to guard it with this explicit mutex lock. In the previous videos, I've already gone through the details about how to test this. I mean, you can watch the previous videos where I've gone through all the details about this, how to test our LRU cache eviction and all. So just to like very quickly recap it, I mean, whenever you are trying to have a very generic way to generic unit test for your multi-thread part of your code, you can use executor service as well as countdown latch. By using executor service, we can control how many number of threads we want to use to execute our critical section of the code which we are testing, and countdown latch will just like how many times that we want to do it. For example, here we are trying to put 50 key value pairs in our LRU cache here, and once this is all done, once we are able to insert 50 pair of values in our cache, then it would be done. Until then, it will wait, and once this is done, we will shut down our executor service, and then finally we will assert here that our LRU cache is having 50 values, even though it is manipulated by 5 sets at a time, and all these values are correct. So this is what the test is all about. So let's confirm that our test case is working out. So first of all, let me actually just create here at line a debug point. Before debug point, let's first run it and see whether it's working or not, because we have changed our get logic in which we are guarding our writing section of that part with the object log. Okay, so our test case is looking good. It's able to assert it. Now let's quickly go through maybe a debug point to see exactly whether it's correct or not. So I put a debug point maybe where not inside this critical section. Maybe I will put it here. Okay. So let's go back to the test case again, and then I can just mark on this debug part. So let me actually expand it a bit. Okay. At this point, let's see, we are able to write to our LRU cache. Let's see, our LRU cache is having capacity of 50, hash table is having 50, which is correct, and the list head node is pointing to value 49, because head is the latest position, and yeah, value 0. So it's perfectly working as it's needed, because we are inserting it 50 times, right, by multiple threads. Still, it's able to maintain this, that the final value, which is put, because at the head we will be having the most recently used, right? So 49th was the last element which was put this time. It can be changed because we are using multiple threads, but it has still maintained it that the most recently one was the last element, which is the head, which is 49, and the least recent is 0, value 0. So if we are trying to like evict anything from this, or add one more element, then the least recently used, which is pointed by this tail node, this value 0 should be removed. Okay. So now let's go back to the exact method. So I will function F9. Okay, so once we do F9, then we are actually at this point. Let me further check it. Okay, so now we are inside the get method. We are getting the key from the hash table, and we are just going through it one by one. Now this is the synchronized part. So here we actually I've just passed it here, so I don't want to debug that part. And as soon as we are done, I think we are going to return the return value. I mean, the reason why I'm going through it is that, I mean, we should try to avoid to access any like synchronized code unless you're unable to fix any threading problem. So by going through this, now we are sure that our code is working correctly and not thread safe. I will remove all these debug points and then confirm that this is all good and our test has passed. So first of all, I will try to thank this guy. I mean, I will just written his name and all. That pointing out this error. So this is how the community works, right? I mean, whatever the code I'm putting here, if you find any type of issues in that, multi-threading is always a very cryptic issue to like find it out, and even fixing it or replicating is like very difficult. But I would just like to thank again this guy who has put this comment, and which help us to improve our code and making our get operation, our LRU cache implement to completely thread safe. So if we talk about this other methods, put and all, because this is we are already guarding it with the right lock from beginning to the end. This is already thread safe. Just that the get part was not correct, and by fixing this bug, now our LRU cache is completely multi-thread safe, and we are just using our own W-link list and a hash map to implement it. So this was all about LRU cache. Again, I mean, I will in the next video we'll talk more about the next problem, which is writing the fixed log parsers. So see you guys all in the next video.